Right. This is example number 2 for the optimization problems. Um, so we're asked to consider an open-top rectangular tank with a square base x feet on a side and y feet deep. Before I go any further, I'm going to show you a picture that I created in Google SketchUp, and I've even imagined the cistern or the tank being underground. I suppose one thing I failed to do is get rid of the top of the tank. But in any case, this gives you some idea. It's just a rectangular prism, or I guess more specifically, a square prism. Okay. Now, its top is going to be flush with the ground. It's going to catch runoff water. The cost associated with the tank involves not only the material from which the tank is made, but also an excavation charge proportional to XY. Okay. So basically, they've done all of the math for us. I'll talk about the different parts here in a second. But anyway, they're telling us this is the total cost. This is what we need to minimize. Okay, so we have to find the x and y to minimize it. So let's go ahead and look at the picture. All right, and let's talk about the volume of this, because this is the one thing that's fixed. It's 1,125 cubic feet. And so we know that, what have I written here? Okay, so the volume, and this is the volume of a prism, it's the area of the base times the height, which is x squared times y, we get 1325. Okay, so that's what they told me. Then I want to minimize this function. This is the cost function, which they gave to me flat out. I've highlighted a couple bits here because you might first look at this and say, oh, you can just combine this. This is 20xy and 10xy, so it's 30xy. This is what we want to end up with. I just want to point out why they wrote it the way they did. What I've highlighted in yellow here is the surface area of the tank. This is the bottom, the x squared, and the 4xy are the 4 side panels. And so that's some cost, 5, whatever that amounts to. And the 10 here, this is going to be the excavation cost, which has to do with y, which is the depth, and x, which is the size of the square. So anyway, this is what we need to minimize. We want to minimize cost, and hopefully you're recognizing that there's a problem. We have this in terms of x and y. And hopefully also you realize, well, if we just replace the y in terms of x, then we could do that. So naturally, we're going to look to this function right here to solve for y. All we have to do is divide by x squared. Okay, so I'm going to rewrite the cost function in terms of x alone. Okay, and so we have the 5x squared plus 30xy. This is y. I replaced it with that. And then I'm going to multiply these together. 30 times 1325 is this. X divided by x squared is x to the negative 1. If you wanted to, you could write an x on the bottom. I've written it this way because I know the next step is to take the derivative. The derivative of 5x squared is 10x. The derivative of this, I'm going to move the negative out front, so it becomes negative 39,750. And then the power of x drops from negative 1 to negative 2. If I were to take the second derivative, I would use this. I'm going to be investigating where this equals 0 or doesn't exist. So I'm going to rewrite it like this. That's going to be more helpful immediately. Just to pause for a second to remind ourselves where we are. We have the derivative of the function. We need to find the endpoints and the critical points. With the endpoints, hopefully you just recognize that x can't be 0 or anything or negative. So we know I should have probably just written x is greater than 0, but that's one of our endpoints. And theoretically, it could be as wide as we need it to be. It would just get really, really shallow and very expensive, I should add. Okay, so this is our derivative from earlier. The critical points occur first, where it does not exist. And as you can see, the only thing that's going to mess this up is if we divide by 0. Okay, so x squared can't be 0, therefore x can't be 0. The other thing we need to consider is what if the derivative equals 0? Okay, and then we've got a bunch of algebra here. So I set it equal to 0. I don't like that denominator, so I multiplied everything by x squared. 10x became 10x cubed. The x squared was missing, and 0 times x squared is just 0. I added 39,000 to each side. I divided by 10, and then I take the cube root. Okay, I'm just going to point out that the cube root of a positive is always positive. I don't have to worry about the negative. Now, so I have 2 endpoints that I need to investigate. The first is going to be 0, which, again, we know that it can't be 0, but if I plug it in, I'm going to get something that's undefined. So that's kind of silly. The only critical point that we really have to plug in is the cube root of 3,975. Now, you'll notice I'm trying to emphasize here that this number is sitting in my calculator. It's the last thing I computed, and therefore, when I plug in, I'm not going to plug, I mean, I could plug in that, but it's just too much work. I could plug in this, but it's not very accurate, and it's more work than just hitting second answer. So this is kind of a really convenient way to do that, and we find that the cost is just shy of $4,000. Really, really close to 3764. Okay, so is this or a max or min? I guess that's something we just assumed that they want us to minimize. I guess it's a minimum. We do need to give some thought to that. I found the second derivative. Okay, the second derivative tells me whether it's concave up or concave down. And if you look at this, if x is a positive number, this is going to be positive divided by positive, which is positive. So I'm going to have 10 plus a positive number, which has to be positive. So that is to say that for positive values of x, we have to have a positive concavity. To say it's concave up means we have a minimum. Okay, so as far as interpreting all this, we just found the minimum cost. We knew that's when x equals this. To solve for y, we use the formula way back from the beginning, which was right here. Okay, and then plug in the x. Again, I would not plug in this approximation, but instead I would either plug in this whole thing or answer if that's what I had done on the previous line.